Thank you for introduction. This is joint work with Klim Efremenko from Ben-Gurion University. And thank you to Arkady for nice introduction. This is a talk in proof complexity. Proof complexity studies proof systems. By means of proof system, we prove that given CNF formula is unsatisfiable, and classes NP and co-NP are different if and only if for every propositional proof system there is a family of hard formulas, and the main research direction is proving lower bounds for propositional proof system proposed by Stephen Cook. And the most studied proof system is a resolution proof system, is to prove that given an CNF formula is unsatisfiable in resolution proof system, we just list several clauses such that the last clause is an empty clause contradiction, and every other clause is either a clause of the initial formula or obtained from previous by resolution rule. In resolution rule, we take two clauses with one variable but with different signs and resolve it. And the main complexity parameters are size, the number of clauses, depth, the length of the longest path, the width is the maximal size of the clause, but the size is a number of different variables in it. And there are a lot of lower bound proved by different techniques, but I want to mention that F2 linear system represents the CNF formula of hard for resolution. And the next proof system we consider in this talk is a resolution of a parity. A resolution of the parity is more or less resolution plus linear algebra modulo 2. It operates with linear clauses that are disjunction of F2 linear equations, or equivalently, linear clause can be considered as a negation of linear system modulo 2. And refutation is a sequence of linear clauses such that the last linear clause in the sequence is a contradiction, and every other is either the clause of initial formula or obtained by one of the two rules. Here, the resolution rule we can take to linear clause with the same linear form, but with different right-hand side in the equation and resolve. And weakening rule from any linear clause, we may deduce any other linear clause that semantically follow from it. And depth now is the maximal number of resolution rules in a path. Width is a maximal rank of negation of linear clause that is used. And it's easy to see that F2 linear system are easier, even for tree-like version of this proof system. And the major open question is to prove superpolynomial lower bound for refutation of this proof system. And importance was described in the previous talk, that is a subsystem of AC0 to Frege. Okay. In this talk, we'll speak also about lifting technique. The idea of lifting is trying to transfer lower bound holds for resolution to resolution of the parity. And by lifting, we mean the standard thing. We have formula phi with variables y1, y2, ym, and take some gadget Boolean function from L variables, and we consider composition. We just substitute for every variables gadget from new copies of new variables. So we have unlifted variables and lifted variables x with two indices. And by the gadget in this talk we mean only stifling gadgets. Stifling gadgets, these gadgets we can fix any value a Boolean, any variable, and then we can choose. We can fix the values on other variables to fix the value of the gadget to be a, regardless the value of the chosen variable. And you can imagine that gadget is majority 3. Of course, for majority 3, we can fix gadget by fixing variables of any two variables. Okay, and for assignment of lifted variables, every assignment of lifted variables using gadget, we can induce an assignment for unlifted variables by the natural way. And one important definition is the following. Let F be a set of linear forms in lifted variables. We want to define the notion that F doesn't restrict the set of unlifted variables. What does it mean? It means the following. For any satisfiable linear system with linear forms F and its solution, tau, if we consider induced assignment on unlifted variables, and after it we somehow change values of variables from set I, we can find another solution that of the system phi that will induce this assignment. Okay. The next notion that is important for us is the notion of closure. It was invented by Efremenko, Garlick, and myself. What does it mean? We have a set of linear forms, and we try to identify the most essential set of linear forms over lifted variables, the most essential set of unlifted variables. And the theorem that there exists such mapping that gets on the input set of linear forms and gets on the output sets of unlifted variables. What properties should have? First of all, that F should not restrict variables out of closure. The second, if we have empty set, then the closure is empty, no essential variables. If we increase the set of linear forms, the number of important variables may only increase. And if F and G has the same span, then they also have the same set of important variables. And the last, we can bound the size of the closure. It is at most the dimension of the span of F. Okay, this is just the theorem of existence, but actually there is explicit construction. And the construction of the closure is the following. Consider set of F and let MF be the coefficient matrix. And blocks here are corresponds to unlifted variables. And we say that the set of linear forms safe if among the columns of this matrix we can find a basis of the span of the columns such that from every block we take at most one column for this basis. And the important property is the following, that if F is safe, then it doesn't restrict Y the whole set of unlifted variables. Why it is so? Because how to solve a linear system with such a matrix? For all unbasis variables, we take arbitrary value, and after it, the basis columns will form square non-degenerate matrix, and their value will be defined uniquely. But in every column we do not control at most one variable, and since we have stifling gadgets, then we can take arbitrary solution in unlifted variables. Okay, and what is a closure? No, assume that that F is not safe, but we try to remove several blocks from the matrix such that the resulting matrix will be safe. By removing the blocks, it's just substitution 0 to the variables of this block. And the closure is the inclusion minimal set of blocks such that substituting zeros to variables from that, we will finally get a safe set. And it can be proved, it's not so straightforward, that the closure is unique, and we denote it by closure of F. And it's rather easy to see that F doesn't restrict variables out of closure, because when we substitute variables to closure, we will get a safe. Okay, and this is example of linear forms, and this example shows that the closure had the following property. Adding one linear form can increase closure more than one. Here it is increased by 2 elements, but actually it can increase arbitrarily. And the idea of amortized closure to have the same properties as a closure, but also to maintain that adding one element to closure counts to increase amortized closure by one element. And the amortized closure is defined as follows. Let Mi corresponds to the set of columns from the ith block. And we say that a set of blocks or set of unlifted variables is coverable if for every block from the set A, we can choose a column such that all these columns are linearly independent. And the amortized closure is the lexicographically maximal coverable subsets of the set of blocks. And in these examples, you can see that adding one linear forms will increase it by at most one variable. Our main result is the following theorem that amortized closure, first of all, contains the plane closure, and it implies automatically that F doesn't restrict variables out of amortized closure. The next properties are exactly the same that we have for plane closure, and additional property, Lipschitz continuity, that adding one linear form increases at most one. Okay. This is our main result, and I wanted to give several applications in lifting theorem. First application is almost the same theorem that was in the previous talk. This theorem states that if G is stifling gadget, then the size, tree-like size of the resolution refutation of the lifted formula can be estimated as exponential of depth of resolution refutation of unlifted formula. We, with Alexeyev, proved that width in resolution can be lifted by stifling gadgets to width in resolution of the parity. And by Dvorak and Shtabakhai, this result was almost extended to the bounded width case. Here in the left-hand side, we consider tree-like resolution of parity refutation of width at most W, and here we consider resolution refutation of width at most W. But it was proved only for strongly stifling gadgets, and this result was used to prove supercritical trade-off. Using our technique, we are able to prove it for the whole class of one stifling gadget. And I can show that this is rather easy, but for simplicity, I prove slightly weaker theorem. I prove it not for tree-like case, but for depths. Namely, I prove that if we consider only proofs of width at most W, then depth of resolution refutation of unlifted formula does not exceed the depth of resolution of the parity refutation of lifted formula. And standard approach is just take a resolution of parity refutation of lifted formula of width W and depth D and convert it to resolution refutation of unlifted formula of width at most W and depth at most H. That's the same as it was. But we use a game approach that was used in our previous paper. We consider games for these two parameters, and we convert game strategy for formula phi in the first game to the lifted game in the second game. Okay, what's a game? A game is as follows. For CNF formula phi and parameter W, we define game for resolution. We have two players, prover and adversary, and they have the common partial assignment. Initially, it's empty assignment, and prover has two possible ways. First way, forget. It means that we can erase some values from assignment row. And query, if the size of the row is less than W, prover can choose a variable, then adversary choose a value to this variable and add to the partial assignment. And for this move, adversary earns a coin. And the game stops, then partial assignment falsifies a clause. And it's well known that adversary has a strategy in phi on W+1 game that guarantees him to earn at least H coins if and only if the depth of resolution refutation of width at most W is at least H. The same game we can define for resolution of the parity. Now the players have the common linear system. Initially, it's an empty linear system or constant true. And the prover has forget. Forget now is from linear system. We can infer any linear system that is corollary of this linear system. And query, if the rank of the current linear system is less than W, prover can choose a linear form and adversary choose the value of this linear form and add equation to the linear system. And the game stops, then the linear system contradicts the clause. And for these games, it can be proved that if there is a strategy to adversary that guarantees him to earn at least H coins, then the depth in resolution of the parity among the refutation of width most W is at least H. So the idea, we take this strategy and convert it in the first game and convert it to the strategy in the second game. We will play two games in parallel and maintain invariant that there is a solution of the current linear system in the second game such that this solution on the amortized closure of the set of linear forms from the system psi equals to the partial assignment row in the first game. And since row partial assignment in the first game doesn't falsify a clause of phi, it implies by the property of the closure that the linear system doesn't contradict the clause of lifted formula. And let us consider steps. Forget step, then psi is replies to its consequence. It's easy to see that the size of the closure of new linear system, the amortized closure of the new system contains in amortized closure of the previous one, and we just make a forget step in the first game. We restrict row to its part. And the case of query, here the two possible cases. First of all, the first case when amortized closure doesn't increase by adding one linear form. Then we do not do anything in the first game, and in the second game we just choose the value correspond that gives our solution tau that make a correspondence between games. And in the second case, amortized closure is increased by one variable. And it is important that by one variable, we make a query in the first game and get an answer. And new assignment be rho prime. And we know by the properties of the closure that there is a solution tau prime of the system psi such that it will induce rho prime. And tau prime will be our new solution, and the answer will be corresponds to it. So tau prime will be solution of the system when we add new equation. And the notion that when each time adversary earns a coin in the first game, adversary earns a coin in the second game as well. And here we use that amortized closure is increased exactly by 1. Okay. And this is the whole proof. And the second application is the following. First of all, consider the following simple lemma. Let phi and psi be two linear systems, and sigma be all solutions of the first linear system. And the statement is the following: that if you take random solution tau, the probability that tau satisfies the second linear system is at most the difference 2 to the difference of the ranks. No, it's very, very easy. And how we extend this? We extend this as following. Now we also fix some partial assignment on the closure of the first linear system, and we consider not all solutions sigma, but only such solution such that the induced assignment extends rho. And then the probability of tau taken at random from sigma that tau satisfies psi can be estimated as 2 to the difference of the sizes of amortized closure. And this lemma was used to improve of our recent result with Yaroslav Alexeyev. The result was the following: that there is a family of formulas phi n with n variables of size of polynomial size, such that any resolution of a parity refutation of phi n has either exponential size or depth omega of n log n. It's interesting because this depth is better than just n. And the formulas phi n in this result actually have lifted structures, lifted setting formulas, and we use the same proof, but in the analysis we use our lemma, and we are able to prove it depths up to omega of n log n. And very recently, less than a week ago, there was published a preprint by Bhattacharya and Chattopadhyay stating the following: that for every positive epsilon, there is a family of formulas phi n of with n variables of polynomial size, such that every resolution of parity refutation of phi n either has size exponential in n to the epsilon or depth omega of n to the 2 minus epsilon. And as far as I understand, they also use the notion of amortized closure and some extension of this lemma. Okay, and open question. No, first open question to go beyond and to the depth and to the square. As I understand, that this is a limit of the current techniques. And another open question is the following. We know that f doesn't restrict any variables out of the closure, or out of the amortized closure, but actually we don't know that f actually restricts something from the closure. The question is if we can somehow define the notion of closure such that we can say that it actually restricts variables from the closure. And if it is so, it may be useful to prove lower bound for general resolution of the parity. Okay, thank you for attention.